All right. Okay. We'll go ahead and get started. Happy Friday, you guys. Another week we survived. And I again I apologize for not yet posting your midterm grades. The thing that's holding me up is, we had there was the AM and the PM, and I just want to kind of make sure that the grading was applied consistently between kind of the different sections and stuff. And so I don't know. It's been taking a little while. I'll get them up soon. Um, I guess before I get into do I know when homework grades are going to be in? Yeah, let me follow up with the graders as well. So um, I'll uh, I'll follow up there also. I apologize for the delay and everything being graded. I don't, I'll, I guess, my idea is always to try to be fair. And so if something comes back and you feel like something was wrong, you can always kind of talk, and we'll try to figure it out. So next week is going to be week 7 already, and we're going to have a midterm on Wednesday. And so I posted this document, midterm 2 topics, on CCLE. And so there's a few things I want to kind of highlight here. Okay. So number one, I've decided. So based on the, I guess, mid-quarter survey. I don't remember whatever it was called, the questionnaire. I read through your feedback, and it confirmed what I suspected, which is we're not doing as well in this online format, or just in general, in terms of like being um, at home and things, and chaos happening outside in the world. So I'm making a few changes, just a few tweaks that I hope will I don't know, I guess, ease a little bit of the burden from the class. This is not what I typically do during a quarter, and so I don't know if anyone plans on writing a Bruin Walk review or something, but don't you guys are getting a slightly toned down in terms of the rigor. It's going to be toned down a little bit, but I don't expect this to be a normal thing that's going to be in the future. So don't post my grade breakdown or something online, and because then future students will be upset that they didn't get the this version of the class. So, but normally I don't like to drop any of the homeworks, because I feel like a lot of the learning happens in the homeworks, and so I kind of like to make sure everybody does all of the homework. But for this quarter, I have decided to drop the lowest of the homeworks. There's going to be 6 homeworks, and I've decided to drop the lowest of the 6, and that means if for whatever reason you don't want to do a homework assignment, you can skip one, and you'll be fine. Okay. It'll go in as a 0, but then the 0 will be dropped. Okay. And with that change, I'm going to bump up the homework weight from 36 to 40%. Okay. And then I'm going to reduce the final exam weight to be 15%. And as far as the final exam goes, I'm probably going to make it approximately the same length as the other midterm exams, so approximately an hour in length. So as far as me thinking of how long the exam should be, so I'm going to reduce kind of the length and weight of the final exam to be comparable to the midterms, and then with the changes, there was a point left over, so I'll bump up your free points up to 2%. So I don't know if you guys have any questions about this, but these are some changes that tweaks I'm going to make for the class this quarter. Again, this is not a typical quarter, and this is not going to be something that I don't expect to do this in the future. I'll probably bump the final exam weight, back to be something higher in the future. So anyway, if you like the class, if you feel like you've learned a lot and stuff, go ahead and tell people about it. You can write me a review or something on any of those class websites, Brew and Walk and things like that. But I'm going to kindly ask that you leave this out of it, just so that future students won't feel like they're getting an unfairly difficult version of the class or something. If that makes sense. Okay. Okay, let me talk about the exam. And again, for this second midterm, I don't want to say it's going to, I'm just toning down the difficulty of the exam from what I probably normally would. Plus, it's also open note, open book. Okay, I still want you guys to study for it. I still think you do need to study for it, and I know that's difficult for some of you, depending on your situations in your personal life. And so, with that in mind, I'm just toning it down a tiny bit, and I'm giving you I think a very detailed explanation of the kinds of problems that you can expect. So that's what we have here. Okay. So there are going to be 2 live exams. So very similar to the midterm. The format, I think, worked fairly well. Most of the feedback in the mid questionnaire for the exam format was mostly positive. Some of you did not like it, but I cannot please everyone. But anyway, so we're going to have one at 10 a.m. and one at 10 p.m. And again, you'll take the exam, and then you'll scan it and upload it to Gradescope. Okay, and then I'm going to just have everybody log in via Zoom, and I will just, I guess, stare at the screen, and that's what we have going on. Yes, is it still okay to use the iPad to write the exam? Yes, that is fine. You can still use the iPad to write on the exam. Okay. Okay, and these are going to be the problems. Detailing them out here. Okay. Are you guys able to hear me okay? I keep getting this warning that says my internet connection is unstable, so I hope my audio is being recorded and being broadcasted. Okay. All right. So then, okay. All right. So number 1 will be numeric gradient calculation for a neural network. Okay. And so this is not, you're not going to be doing the derivatives or anything like that. Okay. This will be a numeric gradient. Okay. Which means, so anyway, I'm going to provide you I'm detailing everything out here. The only thing I'm not giving you is the numbers. Okay. So you can pretty much try out your own practice problems. Okay. Give you a simple neural network, 2 nodes in the input layer, 2 nodes in the hidden layer, 1 node in the output layer. Okay. I'm going to give you the weight matrices and bias matrices, W1, B1, W2, and B2. And then as far as the activation function goes, we're going to keep it real easy. Okay, we're going to have it'll be the identity function, right? So when you apply it, it doesn't change anything. Okay, and then I will provide some input matrix X, some actual values in the matrix T, and then I will also go ahead and do the forward feed part for you and give you the y hat values after you run the values through W1, B1, W2, and B2. So a lot of it will be provided. All you have to do, okay, so part D should be very easy. You just have to calculate. Now you cannot hear me. Okay. I'm not sure what I can do about this. You will have to calculate the loss value, okay, the current parameters, which will be the sum of squared residuals, and then you will perform numeric gradient calculation for one of the matrices, which involves adding a small increment to each value, each element in one of the matrices one at a time, and you'll basically measure what change it has on the loss. Okay, so that'll be kind of your numeric gradient. You'll also have to do so that's one problem. Okay, then you'll also get a maximum likelihood and Fisher information problem. Study these slides that I've highlighted here for an example. Okay, the slides were this, but it's not going to be Bernoulli. Okay, it's going to be a different probability distribution. Okay, so I'll provide a PDF or PMF. I'll provide a few observations, and you're going to find the maximum likelihood estimate of the parameter based on the data. Okay, and then you'll also find the Fisher information of the observed data, right? So this involves taking the second derivative, calculating the expected value with respect to the outcome variable. Okay. All right, and then you'll also have a Bayes classifier problem. Okay. Take a look at lecture 6.1, the Bernoulli binomial example. I think that's going to be good. And then there'll be a handful of conceptual questions. Okay. And you know, this document is just for you guys. All right. Please don't post this online. Please don't share it. It always, you know, every now and then I'll search for my stuff on the internet, and it's always a little upsetting. It's always a little upsetting when I find my things, and I know like 99% of you are honest and are not causing trouble, but it only takes one student to who for whatever reason decides to post these documents that I've asked not to share online, to kind of, you know, make it a sad experience for me. Okay, are there any questions before I get started on today's lecture content, before we go on here? No, we're all good? Okay. So we will, so that'll be that, okay? Will any of the exam content be on the videos? I'm sorry, I'm not sure what you mean by. Will any of the exam content be on the videos? Which exam content? I'm sorry. Will the conceptual questions relate to the required viewing? Oh, the conceptual stuff will generally be things I've talked about in lecture. Okay, so I know I had you guys view additional videos. Those were there to kind of deepen your understanding. I don't think I'm going to ask any like questions that are specific from the supplemental videos that that I posted. Um, but I think, you know, if you watch those things, you'll gain a deeper understanding of the concepts, and so so I think they're helpful, but I don't think I'm not going to intentionally say, all right, this was one thing that was mentioned only in the video, and nowhere else in class. So so that's what we'll have there. I hope that clarifies. Okay. Let's go ahead and get started on today's topic. Okay, and so we're going to continue looking at classification. Today's classification topic is K nearest neighbors. So K nearest neighbors will not be on the midterm exam. Okay, but here it is. Okay, and all right, and so so the idea, okay, is this is pretty much it. Okay, you get some training data. Okay, all of the training data is labeled with a class, right? So you've got some numeric data. Okay, so you've got almost all, not almost all, but a lot of machine learning algorithms have numeric input matrices. Okay, and then some kind of output vector or output matrix. And so if you have categorical data in your input, then a lot of times you have to convert your categorical data into numeric data, and there's a whole discussion on how this should be done. This is also known as feature engineering, which is basically how do you turn your input data into numeric values that can be used for machine learning algorithm. And sometimes that's as simple as just taking each category and turning them into ones and zeros. That's known as one-hot encoding. But then there are other methods as well, and so so that's what. But anyway, what we have is we're assuming we've got a numeric input matrix. That's the training data, and they're all labeled. Okay, all right, and then so the entire algorithm happens when a new test case comes in, and what we do is we measure the distance, generally the Euclidean distance, but it can be modified to be, say, the Manhattan distance, like the L1 norm of the distance vector, or whatever it might be. You're going to measure the distance from the test case, the new test case, to every single other point in the training data. Okay, this can become very computationally expensive if you have lots of training data. So so this is something you have to do. Okay, and then after you've calculated the distance to every single other point, you sort the distances, and then from there you select the K observations with the smallest distances, which is where the name K nearest neighbors comes from. It's the K neighbors, the K observations that have the smallest distances, so they are the K nearest ones. And then the class with the highest representation among those K nearest neighbors is going to be the class that is picked. Okay, and a big question is, how do we pick K? And the general recommendation is to use cross-validation. Okay, and technically we could end the lecture right here because that's all of K nearest neighbors. But I'll work through a couple examples here to kind of explain. Oh, and then here's another slide on you know, what do you do if to resolve ties? Okay, so if there is only two classes and the K that you select is odd, then you'll never get ties. Okay, so if you say let's pick the 5 nearest neighbors and there's only two classes to work with, then you'll either always have kind of a 3-2 split or something like that, right? It's kind of like the Supreme Court or something. You're not supposed to end up in a tie. But there is no hard rule about how ties should be resolved, okay? And some options for dealing with ties, okay? If you do have a tie, which can happen if you have more than 2 classes, or if you have an even numbered K or something. So if you have 3 classes, and let's say you're picking K as 5, it's possible that 2 end up in A, 2 end up in B, and 1 ends up in C. And so you have a tie between A and B with two observations each. Okay, so there's a few ways, right? One is you just say unclassified. Basically, you designate no class. Or maybe for in those situations where you do have a tie, you say you're going to switch to the 1 nearest neighbor. There's never a tie when you have the 1 nearest neighbor. Or you can randomly select among the top tied groups. So you can say, if you have 2A, 2B, and 1C, you can say we'll randomly select between A and B, okay? Or you can say among the top tied groups, so again, if we have 2A, 2B, and 1C, you can say between the A and the B, which one has the closest neighbor, and you're going to pick that, which is not necessarily the same as the 1 nearest neighbor, because it's possible that the 1 nearest neighbor was class C, but the top 2 tiered tied groups are A and B, and you have to pick the closest between A and B. Okay, these are just different options. There's no consensus that says this is the best method. Okay, just depending on the situation and how much computing expense you have to spare, you can kind of pick between some of these. Okay, so here I'm generating some random multivariate normal data with quite a bit of noise and whatnot, and this is just to plot the points, okay? And all right, so here is the data. This is going to be our training data. I've got some red points and I've got some blue points, and then let's say I pick a new observation, right? I'm going to pick a test case. I'm going to say, well, how should we classify this test case? Okay. So here I'm going to put a test case right here. And the question is this going to be red, or is this going to be blue, or what? Okay. So, and the answer, I think I've intentionally picked a lot of these test cases so that depending on what size K you choose, the answer will be a little bit different. Okay, so how does the K nearest neighbors algorithm work? Well, first we have to measure the distance to every single other point in the training data, right? Visually, when you have 2-dimensional data, you can just be like, well, that's stupid, because I can just easily see which points are the closest, right? It's like these points are the closest, or, I can draw a circle around here and just see which ones are the closest. But if you don't have 2-dimensional data, like if you have 17-dimensional data, right? If your data exists in 17 dimensions, and I ask you which observations are the closest, it's not easy to visualize. Okay, you can't. There's not like a hard and fast rule that says, oh, definitely. You can just limit it to a certain range and say these data points are the closest. So, especially in higher dimensional data sets, you just have to measure the distance, right? The Euclidean distance. So you take the difference in x1, you square it. The difference in x2, you square it. You add those two together and you take the square root, right? So anyway, here this represents me calculating the distance to every single other data point. Okay, so I'm not showing the matrix of the distances, but we would do this, and then you know, we would then have to kind of sort them and say, all right, how many, which one is the nearest? And so if I did k equals 1, at k equals 1, okay, and so I've drawn a circle from my test case, we can see that it's red, okay? It's red. We've got one red dot, so we're going to pick red. At k equals 3, I've got 2 red and 1 blue dot, okay? So I'm just kind of keeping odd valued k's. At k equals 3, we still choose red because out of the 3, I've got 2 red and 1 blue. Okay, if I go up to k equals 5, this will become blue, right? So out of the 5 nearest neighbors, I got 3 that are blue and 2 that are red, and so we've got a 3-2 vote for blue. So at k equals 5, it becomes blue. And then at 7, it's also going to be blue. Okay. So this one is not one of the 7 nearest neighbors. This is the 7th nearest neighbor. This one's very close, but it's a little bit farther away. So there's no line being drawn there. Okay. So with the 7 nearest, we have 4 that are blue and 3 that are red. Okay, here's another one, right? So here, this one, what would you guess this would be? Okay, it looks like it's a little bit more like to be red, but let's go ahead and take a look. So we're going to calculate the distance to every single other data point, and then we have to we sort them and we pick the from the nearest. So at k equals 1, we pick red. K equals 3, we pick red. K equals 5, we still pick red. And k equals 7, we still pick red. Okay, it's close. We got 4 red and 3 blue, but it's still red. Okay. One thing to note is that if you pick an unusually large k, okay, and then you just happen to have more blue than red, like, so if my data was split so that I had, let's say, 20 blue and 15 red, okay, 20 blue and 15 red, so I have 35 data points, and then I pick something like k equals 35, okay, then every single dot will be blue, right, because I've got more blue dots than red dots. So, you know, if you pick k to be too big, you've got a useless result. Okay, so here you've got k equals 7, and so on and so forth, and you can keep ramping up k. Okay, this is just some code that will show some boundary regions, and that just shows the effect. I'm gonna have to shrink this so you can see the actual code that's being written in it. And I copied it mostly from this Stack Exchange post here. Okay, and in your next homework assignment, you're going to code up the KNN algorithm yourself, but then what we can do is it is implemented in R using just the KNN function. Okay, so the KNN function works, and this will provide classifications in the form of a model. Okay, but for your homework, I'm going to make you guys do a lot of the work yourself. Okay. Okay, and so this is what boundary regions look like when you have. So this is the same data. So all I've done is I've taken this data and I've put it into this plot, and this is what a boundary region might look like if we have k equal to 1. Okay, and so what happens when you have k equal to 1 is k equals 1 will generally overfit the data, and our data is fairly sparse, so we don't have too much jaggedness, okay? But this probably is not the best classification. Probably, if you had a like if I just kind of, if we look at this and I said try to draw a boundary between red and blue, would probably just kind of draw a line here, and then this red dot would just end up on the wrong side, right? So if like I could draw a straight line, I could just draw a straight line that just chops right through here, okay? Or I might draw a curved boundary that kind of goes like this. I'm not quite sure. You know, what happens down here, who knows, okay? But with k equals 1, you basically get like this Voronoi pattern, and it will kind of this is the same as the 101C content. Okay, so sorry that you're saying this again, but this is what we have. So yeah, so this is what you get for as the boundaries for k equal to 1. Okay, with k equal to 3, and as you increase your k, what ends up happening is you get slightly smoother isn't quite the right word, but the boundaries will be less influenced by lone points off in the wilderness, right? So this red dot kind of probably shouldn't be over here, okay? It is, but the boundary is going to be less influenced by some kind of dot out here, okay? And then this blue dot, which is kind of off on a little too far on the right, kind of ends up getting. So it's not exactly smoother so much as just ones that are less influenced by lone outlying points, okay? As we bump it up, k equal to 5, we get kind of a boundary that's, you know, a little bit more, again, ignoring some of the borderline border civilizations or something here, okay? K equals 7, this is what we get, okay? If I make my the number of training data more dense, okay? So here I've added a lot more data, okay? And I intentionally did it so it's a little bit more mixed and messy, okay? Then, you know, what do we see, okay? So with k equals 1, every single dot gets like its own enclave, okay? So with k equals 1, you know, we see this red dot, which probably shouldn't be over here, okay? This red dot right here will get its own little red enclave. And same with these blue dots. These blue dots, which are out here, you know, it's clearly like red territory over here and blue territory over on this side. But because these blue dots happen to end up over here, they get their own little enclaves, their own little kind of district. And this red dot also gets their own little district. And these 3 red dots, which have kind of veered into blue territory, are getting their own little areas here, okay? So that's k equals 1. K equals 1 is going to often exhibit these funny little zones here, okay? With k equal to 3, okay, now these enclaves don't really exist anymore, okay? Coincidentally, it's just kind of a little bit funny that right around this red dot, okay, there happens to be 2 blue dots, and right around this red dot, it just so happens that this ends up being a little blue enclave with this red dot in the middle, and coincidentally also something similar is happening with these 3 dots out here. But in general, we have a little bit more of a better defined boundary between red and blue here, okay? And as I increase the k, these dots which have ventured into blue territory and these blue dots that ventured into red territory are kind of ignored, and we're drawing again, smoother isn't the right word, but a boundary that is less influenced by any one individual data point. Okay, and here this is what it looks like with k equals 7. And then if you just kind of crank it up all the way to k equal to 20, you're going to kind of get this middle of the road boundary between red and blue. Okay, that will probably have its fair share of misclassifications. And so if you think about the bias variance trade-off, okay, as you increase your k, in general your bias will go up, but your variance will go down. Okay, so this is kind of the overall broad regions between red and blue will be kind of more defined like this. With k equal to 20, you're going to consistently get kind of, you can imagine different dots appearing again, but you're going to get kind of a starker contrast between the red and the blue, whereas with k equal to 1, in the long run, as you do more and more of these things, in the long run, the average of all of your different realizations and different classifications will be correct in the long run. So you'll have very little bias, but you're going to have incredibly high variation because your classification boundaries are going to be entirely dependent upon just the random sample of data that you have. Okay, so with k equal to 1, you've got low bias, high variance. As k gets increasingly large, you're going to have high bias and low variance. Okay, and ideally you want something, who knows what the best k is, but you want something in between. Okay, and the way we're going to kind of estimate is using cross-validation. And with cross-validation, you basically select some of your data points to be your validation set, and using the other data points as your training data, you're going to see how, if you can correctly classify the missing data points, right? Your validation test points, to see if your selection of k is performs well or not well. Okay, so that's what you do with cross-validation there. I guess you guys see this also in 101C, but I'm not sure when. I don't know if everybody has taken 101C yet, right? I think generally it's, you take it at the same time as 102C. But okay, anyway, that's it. That's all I have for you guys today. You'll code the as far as the steps go. It's really just this, okay? And you have, ideally you can be a little bit creative in terms of your implementation of this when you code this up. So that will appear in your next homework assignment, is coding this up. I think it'll be a good exercise as far as thinking through your code and writing this out. Oh, quiz answers. I forgot about that. Today's quiz, it is Friday of week 6. It is D and B. Okay, so first is D as in dog, and the second question is B as in boy. D as in dog, B as in boy. Or Bruin, bear, I don't know. Okay, we'll end a little bit early today. And we'll see you guys on Monday. Have a good weekend, and we'll see you then.